Hello friends, here we are opening up a new series of discussion on molecular spectroscopy. Various set of molecular spectroscopy are essential or versatile tools in any chemical research laboratory, analytical laboratory or for quality assessment. And we will be seeing different kinds of spectroscopy techniques, the fundamental ideas behind and the principles of these techniques, including microwave, infrared, electronic, Raman, nuclear magnetic resonance, and electron spin resonance spectroscopy. And the target group of the series will be mainly graduate level and postgraduate level students. And in this first session, we will be seeing the general idea behind spectroscopy, how the light matter interaction leads or to form a helpful characterization techniques in chemistry.
Yes, let's now see the general aspects of molecular spectroscopy. As was said before, spectroscopy and spectroscopic tools are realized because of the light-matter interaction. So in order to see the details of spectroscopy, we see first light. Light, more technically an electromagnetic radiation, when it propagates in this direction, consists of an electric field in the perpendicular direction and a magnetic field in the other perpendicular direction. So, light, more technically an electromagnetic radiation, consists of an electric field and magnetic field perpendicular to each other, and both are perpendicular to the direction of propagation. And the difference between adjacent or consecutive troughs are called wavelength, and the number of waves passed per second through a particular distance is called frequency. Therefore, energy of an electromagnetic radiation is given in terms of frequency. That is, energy is proportional to frequency and is equated with Planck's constant, and energy is related to wavelength through the velocity of light in vacuum c, which is a constant, and also an expression in terms of wave number is possible, where wave number is defined as the reciprocal of wavelength, that is, number of waves passing through a centimeter distance. So these are the expression for energy of electromagnetic radiation, and we need to have this information in hand to see the details of spectroscopy. Now, arrangement of all these electromagnetic radiations according to the order of wavelength is called electromagnetic spectrum. So, electromagnetic radiation consists of different components ranging from radio waves to gamma rays. The lowest energy in this spectrum shown here is the radio waves with the highest wavelength, and the highest energy component is the gamma rays with the lowest wavelength. Somewhere in between we can see the visible light region, which helps us to see things in colors. Now, after having this introduction on light, let's ask you a question on spectroscopy. What are you looking at through the light? We are looking at matter, more correctly molecules. And why can you see molecules through light, or why spectroscopy is possible? Because light interacts with molecule, and what kind of interaction or how the interaction is possible with light and molecules. And let's now see how light and molecules are interacting each other to help us understanding the molecular structure. So here you've got molecule on one hand and light on the other hand. If somehow it is possible to generate molecular electric field or magnetic field, that is, electric field associated with the molecule and magnetic field associated with the molecule, and we know electromagnetic radiation too consists of those two components, and when the electric or magnetic field component of the molecule overlap with the respective electric or magnetic field component of the electromagnetic radiation, the molecule can now absorb this particular component of electromagnetic radiation to give rise to spectrum. And at that state, we can say the molecule is in resonance with electromagnetic radiation, or the molecular electric field component, its energy, its frequency are in resonance with respective component of the radiation. And let's see how this interaction occurs. You've got molecule possessing certain amount of energy, and when light falls on this molecule, the molecule can absorb certain amount of light, certain component of the light, and can excite to a higher energy state. And now what happens to the light? The light, only a part of the light is absorbed by the molecule, and the rest of the light is transmitted. And now if we look at the light, what can we see? We can see in the beginning before absorption, light consisted of the whole range of electromagnetic spectrum. And now if you look at the transmitted light, you are able to see that a particular component of the electromagnetic spectrum is missing. And why this particular component is missing? It is because the energy difference between the two energy levels, or the amount of energy absorbed by the molecule in order to excite from the lower energy level to the higher energy level. This difference now corresponds to the energy of the electromagnetic radiation, this particular radiation component. You can have absorption of that component of electromagnetic radiation by the molecule. And that instrument or that device which help you to see the light which was absorbed and the amount of light which was absorbed was called spectrometer. And that process, what was happening during the absorption of light by the molecule and the excitation to a higher energy level, all these are treated under the theory of spectroscopy. And now the question is, how these molecules possess electric or magnetic field? Because molecules are molecules, mostly not charged, but how can they have electric and magnetic field? Simply because they move. The molecules undergo different kinds of motion. They have got a lot of motional degrees of freedom. For example, they can move from one position to another like this. That is called translational motion. And they can rotate themselves about certain axis, that is rotational motion, and they can vibrate about their bond length like this. And these different kinds of motions contribute to the energy of the molecule. And these motions have their own significance because this motional energies reflect in several molecular properties. For example, if a lot of energy is concentrated on vibration, that means on bond length, on change in bond length, you can have bond dissociation like this. This vibration happens vigorously because large amount of energy is focused on this vibration, and in the end you can have a dissociation of the molecule like this. So these motions, molecular motions, can have implications on several molecular properties. And the total energy of the molecule is contributed by all the three motions: translational, vibrational and rotational motions, and the electronic arrangement or internal structure of atoms. Internal structure means electronic arrangement or positioning of electrons within the molecule in the molecular orbitals. Among these four components of total energy of a molecule, these three, the vibrational motion, rotational motion and the internal structure, arising due to electronic configuration. All the three energy forms are quantized. Now let's see what is quantization of energy. Quantization can be simply represented by those two pictures. The second picture, for example, represents translational motion. That is, this guy can decide his step size. He can step a smaller step and a longer step. There is no definite amount of energy associated in each step. On the other hand, the first guy, he is representing the rotational motion or vibrational motion or electronic transition from the ground level to a higher excited level. These three motions are quantized. That means energy associated in these three processes are associated with definite amount of energies. This guy cannot extend or shorten his step. His steps are of definite size. Likewise, these three motions, rotation, vibration and electronic excitation, are associated with definite amount of energy. This idea of quantization was based on Planck's quantum theory, that is, light is propagated or transmitted in the form of discrete packets of energy called quanta. And this packet of energy is of definite size, like the step size here. So each of this motion is associated with definite amount of energy. That is why these three motions are quantized. And since they are associated with definite amount of energy, these three motions can be utilized, or energy associated in these three motions can be utilized to understand the molecular structure. They are rotational or vibrational motion or electronic transition, and this understanding will lead us the understanding of the molecular structure. Therefore, now onwards we will be looking at those three things. Seeing the energy levels, here in the lower part you have got the ground electronic state and in the upper part you have got the excited electronic state. And you can see, if you look at this particular ground electronic state, within this given ground electronic state itself, you can see several vibrational states which are marked by this horizontal blue lines. So within the given electronic state itself, the system, the molecule can have several vibrational states, vibrational energy levels. And within each vibrational energy state, you can have several rotational energy states or rotational energy levels marked by the pink short lines here. That means a molecule in a given electronic state has got several vibrational states possible, and a molecule in a given vibrational state can have several rotational states with it. And the energy required for excitation from the lower electronic state to the higher electronic state, that is larger obviously from this picture than the excitation, the vibrational excitation, that is excitation from the lower vibrational state to the next higher vibrational state, and which is larger than the excitation from lower rotational state to next higher rotational state. That means electronic excitation is associated with the largest energy and the rotational excitation is associated with the smallest energy. And therefore, these processes, electronic excitation for example, occurs by the absorption of larger energy component UV visible region of the electromagnetic spectrum. And vibrational excitation occurs by absorbing smaller energy component relative to UV and visible, which is infrared region of the electromagnetic spectrum, whereas rotational excitation occurs by even smaller energy component, that is by microwave radiation. Therefore, the electronic spectroscopy is also called UV visible spectroscopy, and the vibration spectroscopy is called infrared spectroscopy, as well as rotational spectroscopy is microwave spectroscopy. With that, let's now close the general discussion on spectroscopy, and in the next session, we will see the details of rotational spectroscopy. Thank you.